This lesson, we're going to start our discussion on inference procedures that relate to multiple linear regression. We're going to start with the overall F-test, which is kind of going to give us an idea of how good our model is. And this is going to be, we're going to be looking at the ANOVA table. So the overall F-test is going to provide us with an idea on whether there's some relation to look at the variables, or to look at the predictors. So if we think back to our ANOVA and our design of experiments, we looked at the p-value for the treatments to assess whether there was a difference in the treatments or not. We're going to take a similar idea here, but we're going to be looking at terms of whether the covariate, at least one of the covariates, is impacting our response. Okay, so our hypotheses on testing whether the betas are equal to 0, that is, no covariates have an impact, or at least one of the covariates is going to have an impact on the response. This test is going to determine if there's a relationship, again, between the response and at least one of the predictors. So if we reject our null hypotheses, this is going to imply that at least one predictor is going to contribute to the significance of the model. The test is based on the sums of squares of regression and the sums of squared of error, just like simple linear regression that we talked about. That y'all probably should have talked about in Stat 5615. The mean squared for regression is the sums of squares of regression divided by the degrees of freedom, which is the number of regressors in this case. Okay, and our MSE is our sums of squares error divided by n minus p. Again, remember, p is k plus 1, but it's just more common to see n minus p than n minus k plus 1. Again, this is similar to what we saw with our design of experiments, is we're breaking up our variability into the sums of squares of regression and then the sums of squares of our residual or error. So our resulting test statistic is going to be our MSR over our MSE. What that looks like in a ANOVA table is here, where we still have, again, the same properties where k, we can add these to get n minus 1. We can add our sums of squares regression, our sums of squared error to get our total sums of squares. And then our mean squares are our respective sums of squares divided by our degrees of freedom. We get an F value, and then in R or jump, you would also get a P value. I have provided us with, again, the equations for our sums of squares. There was a little mistake. I'll fix that. There's not supposed to be anything. It's our data minus y bar. But before moving on to talking about the overall F-test and the procedure, I just want to quickly give you guys some intuition on what's happening. Okay, so if I was to draw a plot, and let's say we have data. Let me find another marker. Say, here's some data. Our data's in blue. Just drawing a simple linear regression. So this is what we observed. So just our yi's. The most simple thing we can do, that is, if we assume no model, our best idea would maybe to just calculate the mean. So this would be the mean of the y's. Take these up, average, and we'd get this. And so our total sums of squares, what this is doing is it's telling us, it's calculating the distance between our mean and our observation, and we're squaring it. Okay. What our y hat is going to do, or our estimated line, what that's going to do is it's going to find the line of best fit, which maybe might be something like this. Okay, so this is where we're going to get our y hat from. And so what our sums of squares regression is looking at is the difference between this point that we're predicting and this point right here. So if this is a big difference, then that's going to tell us that our predicted model or estimated model is actually describing or better than just if we did something with no model or just taking the average of our data. And so when we have a large sums of squares regression, then our predicted line is going to look very different than our just our overall mean. But notice if we take this purple line and it was to become more flat, then it would look almost exactly like our y bar. And so we would say that our model isn't really contributing to understanding our response, or it's not going to do any better than just taking the overall mean. So we want a large sums of squares residual, and again, we want our SSE, which plays into our MSE, which is our background noise, to be relatively small. That's just to give you guys some intuition as you start to see these results. Hopefully they at least make some sense. So let's move on to the overall FTest kind of procedure breakdown. So we have our hypotheses where we're going to be looking at beta 1 to beta k equal to 0. We're not including the intercept here. You could, but we aren't for the global test. And then we have at least one differs. We have our assumption, which we will talk more about in the coming weeks. We have our F test statistic. K is our number of regressors. P is our number of parameters. We'd get our F test statistic from our ANOVA table along with our p-value, and then we would make a conclusion. So to do this with our, let's do this with our fish catch example. So recall, we're working with our State Fishery Commission, and they want to estimate the number of bass caught in any given lake of the state during a season. We sample a number of lakes, record the number of bass caught. We also are looking at predictors such as the resident density, size of the lake having public access, and then the structure index. What the overall F-test is going to help us determine is if there's a relationship between the seasonal catch of bass and if there's at least one of the predictors that is important to it. Okay, so again, hypotheses, assumptions. Right now I'm just doing this. As we start to learn more, you would actually need plots and whatnot for this. So in ANOVA, or in JUMP or R, we would get, in JUMP, we're going to get this ANOVA table. Typically, up until this point, we have rarely looked at this F-test or F-ratio that's come from our ANOVA table. The only time that we did was with a completely randomized design. But now, we are going to be looking at this F-ratio for the overall F-test. My R users, in your output, you'll see something like this. There's a lot more here. I'm trying to shorten it up for you. But you'll also get your F and your p-value. So our test statistic for here is 39.6. Our p-value is super small. So we're going to reject the null and conclude that at least one of the predictors impacts seasonal catch. We don't know which one yet or which ones are impactful. We're going to talk about that in our next lesson.